We're ready to start section 5.4 on triple integrals. You'll remember that in section 5.3, we took a look at double integrals. We were working with functions of two independent variables, x and y, where the domain was a subset of the xy plane. The function f created a surface in three-dimensional space, and we defined the double integral to represent the net volume of the solid created by the surface over the restricted domain in the plane. We began with domains that were rectangles and then expanded to general regions, and finally to using polar coordinates in the previous section to simplify some functions and domains. We now want to turn our attention to four-dimensional space. We want to look at functions of three independent variables such as x, y, and z. In that case, we're in R4. Our domain then will be some kind of surface out of R3, or three-dimensional space. As we did previously, we'll start with a rectangular shape. In this case, we're going to start with a rectangular solid, which represents, of course, basically a box. And then we will advance to more general three-dimensional solids as the domain. We're going to define what we call the triple integral of a function f of x, y, and z over a rectangular solid or a more general region. In this section, we have several learning objectives. We're going to recognize when a function of three variables is integrable over a rectangular box. This will be our simplest situation. Then we're going to evaluate a triple integral by expressing it as an iterated integral, just as we did for double integrals. We'll recognize when a function of three variables is integrable over a closed and bounded region. This is the more general region in three-dimensional space. It needs to be closed, include its boundaries, and it needs to be bounded, as in not an infinite region. We'll not be looking at improper integrals in this case. We're going to simplify calculations by changing the order of integration of a triple integral. We'll work several examples where we work them in different orders. Then we'll learn how to calculate the average value of a function of three independent variables. Allow me to share my screen and we'll get started. Let's suppose that we start with a function of three independent variables, x, y, and z. This means that we're actually in four-dimensional space because our dependent variable w depends on the value of x, y, and z, which are our independent variables. We're going to start with this function over a rectangular solid box in R3. We can define a rectangular box in R3 by putting constant limits on the three independent variables, x between a and b, c, y between c and d, and z between e and f. In other words, it's much like a Kleenex box, and we're talking about the distance in x being one measure, and the distance in y being a different measure, and the distance in z being a third measure. To make it a box, the measures have to be constants. Then we're going to do pretty much what we did for rectangles in R2. We're going to again divide each of the dimensions along the x, the y, and the z into subintervals. We'll use the letter L for x, the letter M for y, and the letter N for z. For convenience, we're going to take the subintervals of each dimension to be the same length, a regular partition, though technically this is not necessary for the proof. This gives us delta x is b minus a divided by L, delta y is d minus c divided by m, and delta z is f minus e divided by n. This is going to subdivide the general rectangular box into a bunch of smaller boxes. We can call these sub-boxes. Since we have L divisions in the x direction and m in the y direction and n in the z direction, we have L times m times n sub boxes making up this larger box B. So you can see here in the picture that we've got the large box B, and inside we've got one of the sub boxes. And the measure of the sub box is delta X, delta Y, delta Z. And this would be our ijkth box, sub box. We're going to do the same thing we did in the case of a double integral. We're going to take a sample point inside this box. Now, when we did this in double integrals, of course, we were in the plane. So we took a sample point from our rectangular shape. So what we're going to do now is we're going to take some point, x sub ijk star, y sub ijk star, and z sub ijk star. And we're going to find the volume of each sub box, which is delta x, delta y, delta z. And we're going to form a triple Riemann sum and take the limit. Let's take a look at the formula for the Riemann sum now. We have a triple Riemann sum summing over x, over y, and over z. And we take the function value at a particular point and multiply it by the change in volume. dv, or delta v, is equal to delta x times delta y times delta z. So our delta v is equal to, well, since dx and delta x are the same, it's the same as dx, dy, dz, or delta x, delta y, delta z. We define the limit as L, M, and N approach infinity of this triple Riemann sum to be the triple integral over the rectangular box, the larger box, of the function f with respect to a volume differential, dv. And again, delta v and dv are not exactly the same, but they get closer and closer together as we take the limit. Now, if the function f is continuous over the entire box, then the triple integral will definitely exist. We'll mostly use continuous functions, but while continuity is sufficient to say that the triple integral exists, it's not actually necessary. It can have some places where it's not continuous, as long as the function f is bounded over the larger rectangular box and continuous except maybe on the boundary of the box, then the triple integral will still exist. But again, we'll mostly use continuous functions. Just as for single and double Riemann sums, you can choose any point within your sub-box to evaluate the function f of x, y, z. Oftentimes, the midpoint, which in this case would actually be the dead center of the box, so the center with respect to all three different directions, in the very center of the, you'd have to go inside, right, to be in the very center. Those often give the best approximations. Now we want to turn this triple integral, which consists of a 3 integral mark with a single b for the box at the bottom notation, and convert it into an iterated integral where we do one integral at a time while holding the other independent variables as constants. The definition tells us that the triple integral over this rectangular box is equivalent to the iterated integral with respect to x, then y, then z. In fact, we can find that there are actually 6 different ways of writing this integral. We can write it first with respect to x, then y, then z, or x, then z, then y, or y, then x, then z, y, then z, then we can do any possible permutation. And we're going to find that with rectangular boxes, it generally doesn't make much difference. With a rectangular box, the A, B, C, D, E, and F are all constant values. So it doesn't make a lot of difference when you're integrating over a rectangular box. as far as which order you integrate with respect to first. However, when we get to general regions, we'll find that some orders are simpler than other orders. So we'll look at how to evaluate which one might be the simplest. We'll work them in different orders so that we can see the different values and show that they do in fact lead to the same result, but one perhaps is better than another. Let's now take a look at example 1. In example 1, we want to find the triple integral of the function z sine x cosine y with respect to the volume differential dv over a box B, where on the box x is restricted to between 0 and pi, y is between 3 pi over 2 and 2 pi, and z is between 1 and 3. In this case, because these are all constant limits of integration, it doesn't really matter much which one you do in which order. You may, however, decide that you want to integrate with respect to the variable that you think is the easiest to integrate with respect to first. In this case, when evaluating the integrand, if I look at z and I know I want to integrate that, I'd get 1/2 z squared, which is pretty straightforward, but it does have the fraction 1/2. If I were to integrate with respect to x first, the integral of sine x would give me a negative cosine x. And the negative, again, while not difficult, can cause careless mistakes. And then finally, we have the factor cosine of y. If you integrate cosine y, you get positive sine y. So my personal preference would be to integrate with respect to y first, then z, and finally x. Let me go ahead and set that up, and then we'll pause the video while you work it out, and then turn the video back on. So the order in which I would probably do this would be the integral of the integral of the integral. And on the inside, I would go with respect to y first. The smallest value for y is 3 pi over 2, and the largest value is 2 pi. My integrand is z sine x cosine y, and I'm going to go with respect to y first. And then after I'm done with respect to y, I'll go with respect to z first, where the limits of integration vary from 1 to 3. And then because I like to put my negatives at the very end, I'll go with respect to x last, integrating from 0 to pi. Go ahead and pause the video now, work it out in any order that you prefer, and then turn the video back on and we'll compare our results. Okay, the final result that we get is the number 8. Now, let's take a look at the order in which I integrated. And again, in a rectangular box domain, the order really does not matter. You just do whichever one seems to be the easiest to integrate with respect to. In this case, I integrated with respect to y first. So the integral of cosine is sine of y, and z sine x is considered a constant factor. I evaluate between 3 pi over 2 and 2 pi, and the sine of 2 pi is 0, and the sine of 3 pi over 2 is a negative 1. So I get 0 minus a negative 1, which is positive 1. This then gives me a new integrand for the outside two integrals of z times sine of x times 1, or just z sine x. I chose to integrate with respect to z next because I'd rather deal with a fraction than a negative. And so when I integrate z, I get 1/2 z squared. The sine of x and the 1/2 are constant factors, which do not enter into the substitution of the limits of integration. The limits of integration for z go between 1 and 3. And you'll notice that I'm tracking which variable I'm working with respect to by at least writing on the lower limit of integration which variable it represents. The order that the differentials are written in can also help you keep track where you work from the inside to the outside. But I find it's also helpful to have at least the variable mentioned on the lower limit of integration as well. When I substitute 3 and 1 in place of z and z squared, I get 3 squared minus 1 squared, which gives me 9 minus 1, or 8. 8 times 1/2 gives me 4. So the new integrand for the outermost integral is 4 sine of x. Now that I have 4 sine of x, I'm going to have to deal with the negative. So when I integrate sine x, I get negative cosine of x multiplied by the 4, evaluated from 0 to pi. Pull the negative 4 out. Cosine of pi is -1 minus the cosine of 0, which is 1, which gives us -2 multiplied by -4, which gives us 8. Now let's talk for a moment about what this actually means. And the truth of the matter is we don't know. Until we know what the function represents, we can't interpret what the 8 is. In 4-dimensional space, we may not have a physical interpretation. It's not like the double integral, where the value of the double integral represented the net volume between the surface and the xy plane over that restricted domain. However, it could be something like temperature at a certain point in 3-dimensional space, according to some function. So the 8 could represent some temperature at a particular location, or maybe pressure of a system at a particular location, something along those lines. Let's now take a look at example number 2. In example 2, we're simply given an iterated integral, not even the triple integral. Remember, the triple integral symbol is 3 integral symbols with a single region underneath. So in our case, we're starting with rectangular boxes. So we would have a B underneath. This one is an iterated integral, so it does not tell you offhand that it is a rectangular box. However, it is a rectangular box. How do you know by looking at the iterated integral that you are integrating over a rectangular box domain, much like a Kleenex box? How do you know? Again, a box is given by constant restrictions on all 3 independent variables, x, y, and z. And you can tell by the limits of integration that z goes from 1 to 0, y goes from -1 to 4, and x goes from 2 to 3. Since all the limits of integration are constants, this implies that we are integrating on a rectangular box. Go ahead and pause the video to work this one out, then turn the video back on so we can check our work with each other. So before we get started looking at this one, I found what I believe to be a typo. So I believe that the limits of integration for z should have gone from 0 to 1 instead of from 1 to 0, since it doesn't make much sense on a rectangular box to be integrating backwards. What effect do you think this would have on the end result? What result does it have on a single integral? Yeah, that's right. It changes the sign of the answer. So you may, if you worked it from 1 to 0, have the same value, but with the opposite sign that I got. I went ahead and corrected the order to go from 0 to 1. But again, if you went from 1 to 0, let's just wait and see if your answer is completely opposite to mine. In this case, all the limits of integration are constant, so it is a rectangular box. And I went ahead and defined it for you here, which was when I realized they were backwards. This is going to give us 4x squared y minus z cubed as the integrand. We're going with respect to z first. The first term, 4x squared y, does not have a z in it, so it's considered a constant. So we integrate and we just get 4x squared yz. When we integrate the z cubed, we get a -1/4 z to the 4th. And then I evaluated from z equals 0 to z equals 1. I changed color and substituted it in down here. When I simplified, I got 4x squared y minus 1/4. If you integrated from 1 to 0, you would have 1/4 minus 4x squared y, the complete opposite to what I obtained. And then we're going to integrate with respect to y. So we take the new integrand and we integrate with respect to y. The first term, 4x squared y, does have y as a factor. So when you integrate, the 4x squared is held constant, but the y becomes y squared over 2, which gives us 4x squared y squared over 2, or 2x squared y squared. The next term was just the constant minus 1/4, so it becomes minus 1/4 y. Then we evaluate for y between -1 and 4. When I simplified, I got 30x squared minus 5/4. But again, if you did it in the order it was written originally, you would have 5/4 minus 30x squared. Let's now integrate with respect to x. When we integrate with respect to x, we get 30x cubed over 3, or 10x cubed, minus 5/4 x, evaluated between x equal 2 and x equal 3. When we substitute in, we end up with 190 minus 5/4, or if you did it in the order originally written, you would have 5/4 minus 190. In any case, you should come up with 188.75 for the absolute value. If you did it in the order originally written, it would be negative. Now we want to turn our attention to integrating over a general bounded region. Integrating over a rectangular solid box like a Kleenex box is relatively straightforward. But let's face it, this isn't generally the shape of things in the real world. Sometimes they form nice, neat rectangular boxes, such as shipping containers, but that's not typically the case. Most things in the three-dimensional world are, well, shaped like blobs, ourselves, for instance. So we want to be able to expand the idea of the triple integral over a more generalized region. So how do we do this? Well, first, we're not going to call it B for box anymore. We're going to call it E instead. And I can't tell you what the E stands for. I'm not sure. So we have what we call a general bounded region of type 1, type 2, and type 3. The truth of the matter is there's very little difference between the type 1, type 2, type 3, other than which plane they cast a shadow onto, the XY plane, the XZ plane, or the YZ plane. So when we're looking at these, they're going to work very similarly, but these are different types. This also gives you, as well, different ways of integrating, different orders of integration. Let's take a look at type 1. I have two images here for a reason. Both of these are a region E, and we can label this one E as well. The one on the left has a circular, well, what would you call it? The widest part of our blob E casts a circular shadow into the XY plane. So type 1 blobs cast their shadows down into the XY plane, which must mean we have the flashlight pointing down the Z-axis, or possibly up the Z-axis if it's below the XY plane. But it's casting a shadow onto the XY plane. But it's the widest part of the blob that casts the shadow. And in this case, the widest part is circular, so it casts a circular shadow. In a more general case, if you have like a blobby space and you cast a shadow, again, the widest part of E is going to cast the shadow down. I mean, imagine holding something that's irregular like this ice container. And I have a light coming down like this. It's going to cast a shadow, but the shadow is going to go according to the widest part of this particular thing. So the shadow that it casts is from the largest cross section that we have of it. In that case, your shadow in the XY plane may be a blob as well. So it'll be a general region in the XY plane. So we have a four-dimensional situation. We have a function of three independent variables, x, y, and z, and we want to integrate across a blob in three-dimensional space. So our domain is E. That's what we're going to integrate over. But E itself casts a shadow into a plane. Type 1 casts a shadow into the XY plane, which you might expect is probably our favorite. All right. We're going to call the shadow that it casts the projection of the regular solid, not regular, but of the solid in three-dimensional space. The shadow that it casts is called the projection of E into the plane, and we'll label that D, much as we did when we were working with double integrals and we had the domain in the XY plane. Now we can describe our blob, this blue space here, or this irregularly shaped thing over here. If we look at these, we can describe E as the set of all ordered triples, because remember, this is a solid, right? It's some weird shape. It's a three-dimensional thing. It's the set of all ordered triples, x, y, z, such that x and y are from the projection in the xy plane. So x and y are elements of D, the shadow cast by our solid into the plane. And our z value goes between two functions of x and y. Now, the way that these two are drawn, the top and the bottom are flat, but that's not always the case. So let's take a look at this guy. The bottom is flat, but the top is not, it's curved. So it's not necessary that the top and bottom be flat. In fact, many times they will not be. So our top and our bottom are functions of x and y. So they define z as a function of x and y. So our definition of E is the set of all ordered pairs x, y that are in the shadow cast by this solid, and z between the function of x, y on the bottom and the function of x and y on the top. And we often call those u1 of x and y and u2 of x and y. Let's talk about how to write the triple integral over a general region. We start with a continuous function, f of x, y, z, over a general three-dimensional region, E, some general three-dimensional solid. It could be anything. It could be a lamp, all right? Such as described above in R3 in the picture when we had E, where D is the projection of E into the XY plane. So we've got a light shining either down the z-axis or up the z-axis, casting a shadow into the XY plane so that the widest part of our solid casts that shadow. Then the triple integral over E of the function f with respect to dv becomes a double integral over the projection into the xy plane d with a single integral on the inside. So we're converting a triple integral into a double integral and a single integral. The single integral is done first because we work our way from the inside to the outside. And the inside single integral has the function f with respect to z, and it goes from the function u1 to the function u2. So again, we're taking this triple integral over some three-dimensional solid E, and we're going to integrate our function of three independent variables. So this is W as a function of X, Y, and Z. And we're going to do that by first doing a single integral with respect to Z from that lower surface as a function of X and Y to the upper surface as a function of X and Y, with the integrand being our function of three independent variables. Once we've integrated the single integral with respect to Z, Then we have converted it into a double integral. And then, of course, we'll have to convert the double integral into an iterated integral. So then we'll have to do a double integral over the projection. This is what we call a general region of type 1, again, where the shadow is being cast into the xy plane. In a sense, then, a type 1 is one where the flashlight is along the z-axis, and the z is the variable you integrate with respect to first. So whichever axis the flashlight is shining along, that's the variable you integrate with respect to first. And then you're looking for the bottom function, giving you z as a function of x and y, and the top function, z, as a function of x and y. So you're integrating from the bottom to the top. When you're doing this, it helps to have the z-axis pointing straight up so that you can see what surface is on the bottom and what surface is on the top of your solid. Now, let's take a look at one where we were doing something a little bit differently. Let's suppose instead that we were shining the light along the y-axis. So the y-axis in our normal video, the x is coming straight at you, z is straight up, and y goes out this way. So suppose you're shining the light along the y-axis this way, then it's casting a shadow into the xz plane. So the flashlight is lying along the y-axis, either on the negative end or the positive end, shining its light this way, and the widest part of our solid casts a shadow into the xz plane. Then I will want to rotate so that the y-axis is straight up, and then I can look to see what function of x and z forms the bottom surface of my solid, and what function of xz forms the top surface of my solid. So I'll have the y-axis pointing straight up so I can tell what's top and what's bottom. And then I would integrate with respect to y first. Whether I integrate with respect to x or z next depends on the double integral, which one I think is simpler to do. So in this case, again, whichever axis your flashlight is shining down, that's the variable that forms the single integral. All right. If you want to find a longer explanation of that, you can go out to mathinsight.org and look for triple integral shadow method. Let's talk now about a general region of type 2. In a general region of type 2, we have a shadow or projection, but onto a subset of the YZ plane. So in this case, instead of shining the flashlight down the x-axis, we're shining the flashlight along, or wait, I said that backwards. Instead of shining the flashlight down the z, we're shining the flashlight on the x. So we're casting the shadow into the YZ plane. Let's take a look at what one of these might look like. Here's an example of a type 2. You can see now, if you look at this, that the shadow is being cast into the YZ plane. So if I want to be able to find my surface, I need to rotate this, of course, so that the x is pointing up so that I can find my two functions of y and z. So this function of y and z is going to serve as the top, and this function of y and z will serve as the bottom, or vice versa, depending on which way it needs to be turned. So again, we have our function of y and z for the upper and lower on the blob when we're looking at it with the x-axis pointed up. In that case, dx becomes the first differential to happen, the first integral, the inner one. So we have two functions of y and z, the variables that it casts the shadow into that plane. And we integrate the function of three independent variables, first with respect to x, and then we compute a double integral where the double integral is happening on a subset of the YZ plane, this region D that you see cast here as a shadow. Let's talk about a region of type 3 next. A general bounded region of type 3 is the only plane we haven't used yet. We've used the XY plane, we've used the YZ plane, now we have to use the XZ. We did actually talk about it earlier. If I'm casting a shadow into the XZ plane, then the flashlight is lying along the Y-axis. So then if I rotated this picture so that the Y-axis was pointing up, this surface here would be the one on top, so it becomes U2, and this surface here would be the one on the bottom, so it becomes U1. When we get into CalcPlot 3D, I'll show you how you can very easily rotate it so that you have the axis that you want pointing directly up. And this will make it much easier to see the shape of the D that's cast into that plane. Now we're going to go ahead and look at the integral. So in type 3, we're casting the shadow into the XZ plane. So we start with a single integral with respect to y of a function of x and z for the lower limit of integration and a function of xz for the upper limit of integration. Then after we're done, we do a double integral over the shadow cast into the xz plane. Now, the easiest way to do this so that you have the y-axis disappear so you can see the shadow in the xz plane is to hold down the Alt key and press the Y key. That will cause the Y to come in or out of the page, and you'll be able to see the xz plane. We're now ready to go ahead and take a look at example 3. In example 3, we want to evaluate a triple integral over some region of the function 6z squared with respect to dv. E is the region that's below the plane given by 4x plus y plus 2z equals 10 in the first octant. Remember that we have 8 octants. We have above the xy plane 1, 2, 3, and 4, and below the xy plane 5, 6, 7, and 8. So if we want to be in octant 1, we're above the xy plane, we're in quadrant 1, and we're below the plane given by 4x plus y plus 2z equals 10. We want to use the projection into the xy plane to solve. That makes this a type 1. If the shadow is cast into the xy plane, then that makes this a type 1. When we're looking at this, remember that E is the domain of the 3 independent variables. Since our space is under this, this makes sense that it's casting the shadow into the xy plane. That means the z-axis is the one we're shining our light along. We need to figure out what it looks like. So when we're looking at this, we need to have a function of x and y for the lower surface of our image and a function of xy for our upper surface of this solid in order to do the inner single integral with respect to z. So let's go ahead and graph this so we can look at what it might look like. The plane isn't going to give us a lot of information. I mean, okay, it's a plane, but that doesn't help much. What we have to do is restrict it to the space in octant 1. So in order to do this, you want to use in CalcPlot 3D a region. Now you're going to have to cast your shadow down into the xy plane to tell what function of 2 independent variables are. When you're looking into the plane, you've got y as a function of x or x as a function of y. Your 2D image is going to have a top and a bottom as well. Your 3-dimensional surface kind of looks like a 3-dimensional triangular thing. It's not really a prism because it's not regular all the way across, but some kind of three-dimensional triangular surfaced thing. So the top in 3D is going to be the plane, and the bottom, since we have to stay in octant 1, is going to be the XY plane, which is, of course, is where Z is equal to 0. Now, if we want to figure that out, what we need to do is think about the projection of the plane down into octant 1. So it's going to cast a shadow, and in the XY plane, Z is 0. So if we replace Z in the equation with 0, we get a line 4x plus y equals 10. So the plane comes down and cuts through the XY plane at the line 4x plus y equals 10, restricted to quadrant 1, so we can stay in octant 1. Now, if you solve that equation, of course, for y, then you can get that y is equal to negative 4x plus 10. And that will give you a y-intercept of 0, 10, and an x-intercept of 5/2, 0. So we know that it is touching the x-axis here at 5/2, and we know that it is touching the y-axis out here at 10. All right? So now we know sort of what it might look like in the plane. Let's take a look at an image of that. I thought I had it somewhere, but I'm not seeing it. Here it is. All right. So what I'm seeing now is this image in the plane. This is the shadow cast by it. Let's take a look at this region out on CalcPlot 3D so I can show you how you can find the projection in the plane. Now remember, you always have to take the widest part of your blob to cast the shadow. Make sure you're taking the widest part. So here's our region. You can tell it does have triangular sides on it, but it's a three-dimensional object. And in order to see this in the XY plane, I need Z to disappear. So to get Z to disappear, you can do Control Home, or you can hold down the Alt key and hit Z. When you do that, then you can see what it looks like now in this plane. So when we're looking at this, you can see that I've got the line y equals negative 4x plus 10, and it's hitting the x-axis at 5/2 and the y-axis at 10. So this is my region D. This is the widest part of that plane casting a shadow. This is the shadow that it casts. Since that's the shadow that it casts, then we need to figure out how to get the function of x and y for the base and a function of x and y for the top, for the single integral. The base, of course, is where, well, the xy plane is, and z equals 0 there. What about this surface? Well, this surface is given by a plane. We can take the equation for the plane, which is right up here, and we can solve 4x plus y plus 2z equal 10 for z. When we solve that for z, we get the equation for the top surface of our region. Let's go ahead and take a look at this so that you can see again that it is in fact the top surface. That plane that you see there, and I'm going to take the box off, just hit B to get the box off. You can see that the top surface is that slanted plane. The back side of it is perfectly straight, all right? Right there, it's perfectly straight, not coming down at an angle, because it's only in quadrant 1. So when we look at this, we're going to use this plane equation, solve for z, as our upper limit of integration. The lower limit of integration for the single integral is going to be z equals 0. And then we have our function on the inside. This allows us to do the single integral But then we need to think about the shadow that's cast. We've already talked about how the shadow is that triangle given by the line y equal negative 4x plus 10. So if we're looking at this, we could integrate with respect to x first or y first, it doesn't matter, but you need to write one of the variables as a function of the other. And we've already got one as a function of the other because I've already solved this for y equal negative 4x plus 10. And that gives y as a function of x. So what is the lowest value of y in this shadow cast by our surface? Well, the lowest, of course, is just the x-axis, so y equals 0. The upper is given by this surface right here, which is the line. This means that y is going to be between negative 4x plus 10 and greater than equal to 0. What about my x's? Well, x goes from 0 to 5/2. So that will give me my outermost limit of integration. So let's see if I can find where I did the integral. Here we go. So now we've got our limits of integration. X is between 0 and 5/2 on the outermost. Y is between 0 and the function of x, 10 minus 4x. And z is between 0 and the plane equation solved for z. So our triple integral becomes from x equals 0 to 5/2. And then we have the integral from y equals 0 to 10 minus 4x. And then we have the integral from z equals 0 to z equals 5 minus 2x minus y divided by 2. And our integrand, if I remember correctly, was 6z squared. Yes. So we have 6z squared. All right. And we're going to integrate the inside integral since it's casting the shadow into the xy plane. It's with respect to z first. Then we wrote y as a function of x, so y is second, and x will be last. The difficult part is getting the iterated integral written down so you know in what order to do things. Let's take a look again at CalcPlot 3D before I turn you loose to work on this one. Take a look up here at the 2D trace plane. Remember, you get the 2D trace plane by clicking on the third graph icon with the blue dot on it. You can see here that you've got your shadow cast into the XY plane. So the trace plane is giving you the projection of the solid into the plane. Now let's go ahead and pause the video while you work this one out, then turn the video back on and we'll compare our results. Let's go ahead now and take a look at the work that we've done. So in this particular problem, we ended up with the integral from z equals 0 to 5 minus 2x minus y over 2 of the function 6z squared dz. Then on the outside of that, the integral from y equals 0 to 10 minus 4x with respect to y. And after that, the final integral from x equals 0 to 5/2. When we work the inner integral with respect to z, we integrate 6z squared to get 6z cubed over 3, or 2z cubed. When we evaluate between 0 and the plane, which forms the upper surface, the best thing to do is to leave the expression in the cube. So we get a 2 multiplied by the quantity 5 minus 2x minus y over 2, all raised to the third power. This becomes the integrand for the outside double integral. In this case, we're going to do the integrand with respect to y next. So then we will do a u substitution by letting 5 minus 2x minus y over 2 be equal to u. This is going to be with respect to y, so we need to find du dy, which just turns out to be a negative 1/2. We abuse the notation by solving for dy, which gives us that dy is negative 2 du. We can actually change the limits of integration. When y is 0, based on our definition of u becomes 5 minus 2x. When y is 10 minus 4x, using our definition of u, we end up with u equal to 0. This means that we're integrating now between 5 minus 2x and u equals 0 of negative 4u cubed. Now, because we have a negative, and because the limits of integration kind of look backwards, we could take care of the order of the limits of integration in the negative in one step. By switching the limits of integration from 5 minus 2x to 0 to 5 minus 2x, we take off the negative on the integrand and it becomes 4u cubed. When you integrate, you get 4u to the 4th over 4, just u to the 4th. Again, when you evaluate, it's best to simply leave it as the quantity 5 minus 2x raised to the 4th power. This becomes the integrand for the final iterated integral on the outside, the integral from x equals 0 to 5/2 of the quantity 5 minus 2x all to the 4th power dx. Let's do another u substitution, where u is 5 minus 2x, so that du is negative 2 dx, and dx is du over negative 2. Then we can change the limits of integration. When x equals 0, based on our definition, u would be 5. And when x is 5/2, u turns out to be 0. By introducing these into our integral by substitution, we get the integral from u equal 5 to u equals 0 of u to the 4th times du divided by negative 2. But we've got another negative in our integrand, so we can switch the limits of integration and pull the 1/2 out so that it becomes 1/2 the integral from u equals 0 to 5 of u to the 4th du. This will give us u to the 5th divided by 5 multiplied by 1/2, or 1/10 u to the 5th between 0 and 5. And when you substitute in the final values, you should come up with 625 divided by 2. Again, we can't interpret what this means until we know what our function of the 3 independent variables is. Until we know what f of x, y, z represents, we cannot interpret this particular result. Let's take a look now at example 4. In example 4, we want the triple integral over a region E bounded by 2y squared plus 2z squared minus 5 equal x, and the plane x equal 1. Our function is y times z. This is our function of 3 independent variables, x, y, and z. The fact that it doesn't have an x in it doesn't make it any less a function of 3 independent variables. We're told to use the projection into the YZ plane, which means it's type 2. If the projection is into the YZ plane, we're casting our flashlight along the x-axis so that the shadow falls into the YZ plane. Let's go ahead and graph this one and take a look at what it looks like so that we can get an idea of what the widest part of our shape looks like. So one region, of course, is a paraboloid, which is symmetric around the x-axis, which is one good reason to shine the flashlight down the x-axis. Our other region is a plane at x equal 1, which slices through this paraboloid, this circular paraboloid, creating a circle. Now, this circle is occurring at the value where x equal 1. The widest part of our solid is right here where the plane and the paraboloid intersect. So the widest part is going to be the intersection of those two curves. Let's take a look at it out on Calc Plot 3D. When you're looking on Calc Plot 3D, you have a solid created by the bottom of the paraboloid up to that surface where x equals 1. That's the plane. Then if you want to see what it looks like by casting your shadow along the x-axis, then you want to take the x-axis out of it so that the shadow goes into the YZ plane. Hold down the Alt key and hit the X key. And now you can see the circle that we've got going on here. However, it's not entirely clear what the radius of the circle is. In order to find that, we need to find that intersection between the paraboloid and the plane x equal 1. That will give us the widest part of our surface, which will give us the shadow that is being cast. In order to do that, we set the two equal to each other. We have x equal to 1, and we have the paraboloid equation here. So we set x equal to 1 in the paraboloid equation, which gives us the function 2y squared plus 2z squared equals 6, or y squared plus z squared equals 3, which is a circle in the YZ plane of radius square root of 3. This is where the paraboloid and the plane meet. So x is not equal to 0 here. It's x equal to 1. So the actual radius of the widest part of our region is the one here where the radius is square root of 3. Then in order to determine, since we've now cast a shadow into the YZ plane, our flashlight is along x. So we want to integrate with respect to x first. We need to know what the lower limit of integration and the upper limit of integration is going to be on our single integral done first. To do that, we want to come over here and we want to rotate so that x is pointing straight up. If we point x up, then you can tell by looking at the solid created by the bottom of the paraboloid up to the plane that the lower surface is given by the paraboloid and the top of my solid is given by the plane x equal 1. This gives me my limits of integration. I will need to go ahead and solve the paraboloid for x, but I believe it was solved for x to start with. X equals 2y squared plus 2z squared minus 5. That gives us the limits of integration for the inner integral, which is going to go on the bottom from the paraboloid, 2y squared plus 2z squared minus 5, to the top, the plane where x equals 1, of our function of x, y, and z with respect to x. Next, we will do the double integral of the shadow cast by that intersection of the two surfaces, the widest part of our blob. And it casts a shadow, a circle of radius square root of 3, into the YZ plane. Because it's a circle, polar coordinates make sense. If we're going to do polar coordinates, though, normally we're in the xy plane, so x is r cosine of theta, y is r sine of theta, and r squared is x squared plus y squared. But we're not in the xy plane, we're in the YZ plane. In the YZ plane, z takes the place of y, and y takes the place of x. So y becomes r cosine of theta, z becomes r sine of theta, and y squared plus z squared equals r squared. We know we want to go all the way around the paraboloid, so theta goes from 0 to 2 pi, and r goes from 0 to the square root of 3. It's a solid region. So when we're looking at this again, by coming over to CalcPlot 3D and looking at that particular one, if you again rotate it so that x is coming out, let me see if I can get it to go exact. Oops, it's rotating. Stop, there we go. You can see that the z-axis is straight up, so it becomes, in a sense, the dependent variable, and y becomes the independent variable. So y takes on the role of x as r cosine theta, z takes on the role of y as r sine theta. Once we have this written down, Then we're ready to go ahead and write down what our iterated integral is going to be. Let's go back and find out again what our function of x, y, and z is, which is y times z. And so we're going to do the single integral first, and then we will convert things into polar coordinates in order to do the double integral. You can leave them in the regular coordinates that they're in right now, rectangular, to do the single integral. And after you're done, convert what's left into polar. Go ahead and pause the video to work out the single integral, then turn it back on and we'll get down the coordinates for the polar next. So again, to evaluate the inner single integral, we integrate yz, which is a constant as far as x is concerned, which gives us xyz. We substitute between the values for x, 2y squared plus 2z squared minus 5 for the lower limit and x equal 1 for the upper. When we multiply it out, we get 6yz minus 2y cubed z minus 2yz cubed. We do have a common factor of 2yz, and it actually helps here to go ahead and factor that out. That will give us 2yz times the quantity 3 minus y squared minus z squared. Now, the reason this is helpful is because we're about to convert into polar coordinates. When we convert into polar coordinates, we know that y squared plus z squared equals r squared. So when we're doing this, we can take this expression here and think of it as 3 minus y squared plus z squared, which becomes 3 minus r squared. And then to convert our y and z, we simply go ahead and rewrite this now in polar coordinates as the following. We will get the integral, iterated integral, from theta equals 0 to theta equal 2 pi. And then the inner integral become the integral from r equals 0 to the square root of 3. 2 stays 2. Y becomes r cosine of theta. And z becomes r sine of theta. And then we have 3 minus r squared. And then, of course, we have our polar coordinate differential. dA, instead of becoming dx dy or dy dx, becomes r dr d theta. So now we have r dr d theta. And the next thing, of course, is to multiply it out so that you have something a little bit simpler to work with. I would probably go ahead and integrate with respect to r, but you could integrate with respect to theta first. Since these are both constant values, the order does not matter. You're actually integrating, of course, on a rectangle. So, or a rectangular polar rectangle. Go ahead and pause the video to work out the next steps, then turn the video back on so we can compare. Once we have our expression, we can continue to keep cosine theta, sine theta as a constant since they don't depend on r by factoring them out and distributing the rest, which leads to 6r cubed minus 2r to the 5th, the quantity times cosine theta, sine theta. Since cosine theta, sine theta is a constant, we just integrate the 6r cubed minus 2r to the 5th, which gives us 3/2 r to the 4th, minus 1/3 r to the 6th, now evaluated between 0 and square root of 3, the limits of integration for r. When we put these into our formula, we can reduce things to 9/2. This gives us the integral from theta equals 0 to 2 pi of 9/2 cosine theta, sine theta, d theta. Then we can do a u substitution. When we do our u substitution, I chose to let u be sine theta, so the derivative would be a positive cosine of theta d theta, which I do have in the integrand. Then when I converted the limits of integration, when theta is 0, sine of 0 is 0, but when theta is 2 pi, the sine of 2 pi is still 0, which means that my integral becomes the integral from u equals 0 to 0 of 9/2 u du. But if the limits of integration match on a definite integral, then the value of the definite integral is 0. And again, we can't interpret this without knowing what that function of 3 independent variables means. We have one more example that we want to work in part 1 of the video series over section 5.4, and that would be a type 3. Let's go ahead and take a look at type 3 now. In example 5, we're going to take the problem that we just worked as a type 2 and now work it as a type 3, with the projection being cast by the widest part of our solid, but into the xz plane. When we're doing this, remember that we have a solid that is the space between a paraboloid and the plane x = 1. If we want to work it as a type 3, then we need to be casting the shadow into the xz plane. So our flashlight is coming along the y-axis. This means our single integral on the inside will be done with respect to y first. Let's go ahead and look at CalcPlot 3D so we can see what the projection looks like. This will help us to determine the region D. I've restricted the paraboloid to going up to x = 1. Now our solid, of course, is simply the paraboloid with the circular top, but it's not really possible to get the plane to only graph on that circle very easily. So the next thing that we want to do, of course, is we want to take the y out of our picture so we can see the projection into the xz plane. Hold down the Alt key and press Y. Now you can see the projection of the widest part of it into the xz plane. It's clear that we have on the right x = 1, which is our plane, and on the left the paraboloid. This, however, gives us a two-dimensional shape for our double integral, which consists of a right opening parabola. We'll need to find the equation here for our right opening parabola in terms of x and z. Let's go ahead and look now at our work again. This is our region right here, which is projected, of course, when y is equal to 0. By setting y = 0 into our equation, we get x = 2z² minus 5, which is the equation of a right opening parabola in the xz plane, where x is now the independent variable and z depends upon x. This opens, of course, to the right. Now, since we're shining the light down the y-axis, which is coming out of the board when we're looking at the xz plane, then we're going to integrate with respect to y first. So when we're doing that, we need to come up with an equation that represents this, the change with respect to y. So to do that, we're going to return to our picture and we're going to rotate it until the y-axis is pointing up. Oops, got it going the wrong direction. And once I get my y-axis going up, then I need to tell, of course, what is my surface on the bottom and what is my surface on the top. And of course, it's still the parabola. When I'm looking at this now, what I can do is I can solve the equation, the original equation for y, which would give me, of course, y² equal to 1/2 of the quantity x minus 2z² plus 5. To find the upper half and lower half of the parabola, I take the square root of y², which gives me plus or minus the square root of that value. Now, when I'm looking at this, the upper half is going to be the positive root and the lower half will be the negative root. This is my function of x and z that gives me the region D in the xz plane. When I'm looking at it then, I need to go ahead and evaluate between this function of x and z, the lower arm, which is the negative arm, to the upper arm, which is the positive arm, with respect to y. If we're trying to then integrate on the other, we have, in this case, x as a function of z equal to 2z squared minus 5. So if we rotate, we end up with x going between 2z squared minus 5 on the low end to 1 on the high end. Then we can integrate with respect to z by setting that on our value here, and that gives us, of course, that z squared is between or less than equal to 3, so z is between negative root 3 and root 3. That's the value of z on the parabola. Now let's go ahead and figure out what the triple integral will look like. And again, if you're confused about how we're getting these values, we're looking here on the intersection between the two, not in the xz plane itself. The widest part is right here where they intersect, and that's where x equals 1. So in the equation, I replace x with 1 and solve, and this tells me that I've got z between negative root 3 and root 3. This would become the iterated integral that we would evaluate in order to find the triple integral of yz with respect to the volume differential. This integral is not nearly so nice as the one we did before. In general, you'll find that the easiest shapes to integrate across are rectangles, followed by circles or semicircles. Those are the easiest shapes to have for your projection to integrate on. Let's go ahead now and look at some applications and final notes on triple integrals. Our final notes on triple integrals are that there is another possible method that can be done. It's called the cross-section method. I'm not going to teach the cross-section method because I found the shadow method to make more sense to most students. But if you want to learn about the cross-section method, go to mathinsight.org and look up triple integral cross-section method. Note that we can get the volume of our three-dimensional domain solid by setting the integrand to be 1. If we set the integrand to be 1, this will give us the volume of that three-dimensional solid that we had before. This is similar to what we did in the case of a double integral, setting the integrand to be 1 to get the area between curves. Let's take a look at example 11. In example 11, we want to find the volume of the solid E from example 3 by evaluating the triple integral with an integrand of 1. E is the region below the plane 4x plus y plus 2z equals 10 in the first octant. Remember, this was the shape with sort of the triangles on all sides. So again, we're going to integrate with the same limits of integration and convert our triple integral into a single integral followed by a double integral, which becomes an iterated integral. Go ahead and pause the video to find the volume of that solid, and then turn the video back on and we'll compare our result. So when we integrate the integrand of 1 with respect to z, we just get z. Then, of course, we substitute the limits of integration from 0 to the quantity 5 minus 2x minus y over 2, which gives us 5 minus 2x minus y over 2. Then we'll integrate this with respect to y, giving 5y minus 2xy minus y squared over 4. We evaluate this from y equals 0 to y equal negative 4x plus 10. When we multiply everything out and simplify, we're left with a new integrand of negative 4x squared minus 20x plus 25, integrated with respect to x from x equals 0 to 5 halves. This gives us negative 4/3 x cubed minus 10x squared plus 25x. Then we substitute in our limits of integration, and we get a final value of 125 divided by 6. This is the volume of what we see when we're looking at this region right here up to the plane x equal 1. That's the volume of our paraboloid region. Now let's take a look at finding the average value of a function of 3 variables. Now recall that we did this for a function of 2 variables by evaluating the double integral over a region on the plane and then dividing by the area of the region. Similarly, we can find the average value of a function of 3 variables by evaluating the triple integral over a solid region and then dividing by the volume of the solid. If we suppose that f of xyz is integrable over a solid bounded region E with positive volume V of E, then the average value is given by the triple integral of the function with respect to the volume differential divided by the volume of the value. Let's go back to example 3 again. We evaluated the triple integral over E, which is our parabola cut off by the plane x equal 1, and our function 6z squared. When we evaluated this in example 3, we got a value for the triple integral of 625 divided by 2. From the example we just did, we found the volume of that bottom of the paraboloid to be 125 divided by 6. That means that we can now find the average value of this function. Go ahead and pause the video to work it out and then turn it back on. This one doesn't take very long. When you're done, you get that the average value of the function of 3 variables is 15. We don't know exactly what this represents because we don't know what our function of 3 independent variables represents. This is the end of part 1 on section 5.4 triple integrals. In part 2, we simply work more examples, changing the order of integration by looking at the projections of each of the solids into a different plane. If you need more practice on this, go ahead and watch part 2. If you feel like you've got a handle on it, then you're ready to proceed to the video over section 5.5.